Good evening. Welcome to the Tucson Amateur Astronomy Association first Friday of the month meeting for our November. This is our member meeting, our monthly member meeting, and we have people in person at Stewart Observatory at the University of Arizona for this meeting. We also have members who are on Zoom. And we have guests who are on social media, and we will be later posting the video for this, so it will be accessible later by video as well. We need to ask people in the room that they not talk at all during the meeting because Zoom will pick up your communication. It might not pick up clearly what you said, but it will definitely pick up the noise of the communication. So we ask people that are in person at the meeting not talk during the meeting. But we're delighted to have everyone here, and we're always delighted to have guests that are on social media with us that can learn about our club and learn about some of the wonderful things that we do and interesting things that we do. So we welcome everyone. We will have a presentation tonight, and then at the end of the presentation, we will take questions. If someone does not understand what the speaker said at that point, or if they don't understand a slide, then if you're in the audience in person, you can raise your hand. Otherwise, we will try to catch those questions that come in typed in through the chat if you're Zoom, and that are typed in through social media if you're on social media. So we will try to answer those kinds of questions immediately. And then other questions, we will kind of see how it goes in terms of timing and the pace of the presentation. So some might be answered during the presentation, but anything that's not dealt with during the presentation will certainly be dealt with at the end. So we will get everybody's questions everywhere. And we're always interested because we always come up with, different perspectives from the questions that we get. Tonight, we're going to have a speaker presentation, then we'll have some awards that will be given, and then we will be adjourning the meeting for our people on social media and also for our other members who are attending, because tonight we're going to try again viewing through the Stewart Observatory telescope tonight. The 21-inch scope will be open tonight from 7:30 to 9 for people who are here in person. And the University of Arizona astronomy students are spending their time operating the telescope for us. Now, we tried this for the first time in a long time last month, and it was cloudy last month. But we have high hopes for tonight that nothing will happen weather-wise all of a sudden to interrupt our possibilities for viewing for tonight. And for members who are here in person, there will also be refreshments after the meeting. So we're going to start with our speaker. We do ask that that people, as I said before, who are on social media or who are attending via Zoom, that you type in your questions, and then when there are questions in the audience, we will all need to be a bit patient because I will need to walk around with a microphone and take the microphone to each person. So there's always a little time lag with that from questions with the audience. Tonight, we're very pleased to have Virginie Faramez, who received her PhD a number of years ago, not too many years ago. I didn't mean to imply that, but enough years ago that she's had some tremendous experience in astronomy research. And if you read the biography that we sent out for her, she's lived in a number of different countries and worked at really prestigious astronomical places in those countries and done some significant research. So we're just delighted to have her with us tonight, and just so pleased that she's willing to spend some time with us. So, Dr. Fairmess.
Thank you so much. Thank you for the invitation. I'm going to pull this one a little bit up. Okay. Everyone can hear me? Okay. So tonight I'm going to introduce you to a little bit of an overview of my work and how everything is connected from pretty much icy comet belts to the habitable zone. And in particular, I've been asked to talk about ALMA, because like some people were really interested in that, and I use this facility. So I'm very flexible with this presentation. I think I'm going to spend a little bit more time on the ALMA part of it, and we'll see. And I will pause once this part is over so that I can have questions, and then we will move on to the rest. So there are famous tools to hunt planets, and I guess as amateur astronomers, you've heard about those. This one is the radial velocity. This is the one that we use to detect the first exoplanet, 51 Peg B, and it relies on the wobbling of a star due to the presence of a planet. It's dynamical. And if you take a look at the spectrum of the star, what's going to happen is when the star recesses, you're going to have a Doppler effect pretty much. When it recesses, the wavelength is going to be larger, so it's going in the red wavelength, and when it comes close to you, and when it comes close to you, it's accelerated, and you see bluer wavelengths. So that's probably one of the most famous and one of the most productive. The second one, and especially with the TESS telescope, produced a lot of exoplanets in the past few years. This is what we call a transit. So you have a planet transiting in front of its star, and if you take a look at the luminosity of the star as a function of time, you have a little dip when the planet passes in front of it. Of course, the kind of dips that we're having are very, very small, and we're always developing more performance instruments to see smaller and smaller planets. And finally, there's the direct imaging. So the direct imaging, we don't have a lot of planets actually detected to that, but it's a method that is probably the method that is being developed the most at the moment, because when we directly image a planet, we can get photons from this planet, and we can start analyzing this light that comes directly from the planet and infer whether there are, I don't know, molecules or even life on it. So at the moment, what we do, and I'm going to replay this video, is that we put what we call a coronagraph in front of the stars so that we can have planet appear. And we use a whole other set of methods to compensate for the atmosphere, because a planet can look like one of those little wobbles. But yes, it's a very promising method, and I will talk about it in a few slides, but there are future instruments that will be devoted to directly image planets in the habitable zones of their host stars. For now, we're seeing things that are pretty much several tens of AUs, one AU being the distance between the sun and Earth, an astronomical unit. But there's a less known technique, which consists in looking at what we call debris disks, and take a look at their shape. So debris disks are leftovers of planet formation, planetary systems formation. It's everything that did not enter in the composition of planets. So you're having depending on where it is located, how far it's located from its star, you're going to have maybe asteroid belts, but the further you go away, then you have icy comets, like these giant dirty snowballs. And there's actually lots of things that happens in there. You can have, as shown on this image, you can have collisions. You have a planet also that is right there, and you can see that it's right at the edge, and it's going to shape the edge. And there's an idea there that planets are going to set their dynamical imprint on these debris disks. And that's one of the techniques that you can use. You can actually take images of those and look for asymmetries and signs of shaping by planets. The idea is the following. So if you take the Earth and you have one Earth mass, you have one Earth surface. Now, if you divide this Earth into two, you have in mass, you still have one Earth mass, but in terms of surface, this time you have 1.26 Earth surface. And if we push this a little further, if we put one Earth mass in kilometer-sized asteroids, then you have 6,000 Earth surface. And finally, if you put this Earth mass into millimeter-sized dust grains, which is what we're trying to observe, you have 6 billion Earth surface. So from there, it's easy to understand that when you're trying to directly image a planet, you're trying to look at a point source. But when you're looking at a disk, you're looking at a multitude of point sources, and collectively, they have more surface than one single planet. And that's why it's very advantageous to take a look at those. So yes, like I was saying, planets shape disks. These are images. Some of these images are by Hubble. So the top left is called the moth. You know, we like to give little nicknames to these shapes that we see. So it's pretty much, it's a disk that is in edge on, and you have all this, it's deformed actually. Underneath you have HD 141567, so it's still an image by Hubble, and you can maybe see the spirals in there if you look closely. In the middle top we have Beta Pictoris. So Beta Pictoris is one of what we call the fabulous four. We had like there were 4 stars around which debris disks were first discovered through infrared excess, because these little grains, they will impart an infrared excess on your star. So if you take a look at the spectrum of your star, you will have at some point, you expect it to have a nice slope in the infrared, and suddenly boom, you have a bump. And this is how we know that these disks are there. And there were 4 stars initially that were around which debris disk was detected. So Beta Pictoris was one of those. Fomalhaut was one of those, if I'm correct. And then there was Epsilon Eridani and Vega. Vega was the very first one. But on the Beta Pictoris image, luckily there's a little hint in the lower panel that tells us there's a secondary disk that is inclined as compared with the primary disk. And that's an asymmetry. That's a hint that we're having a planet in there. On the bottom middle panel, so we have Fomalhaut. And for Fomalhaut, on this image, you can see a little yellow-orange lozenge, and that tells you, that indicates the location of the star. And the white circle indicates the geometric center of the disk. And as you can see, they do not coincide. So of course, when you take a look at a ring, a debris disk that is in shape of a ring, because it does not necessarily appear face on, you can have like some projection effect if it's inclined with the line of sight. And so what you will see is an ellipse. But in this specific case, even if deprojected, the disk is actually an ellipse. It's not just a projection effect. There is an actual geometric effect of the disk being intrinsically eccentric, and this is indicated by the fact that the star does not coincide with the center of symmetry of it. So that tells us again that there has to be a planet shaping that. And there are on the right panel, so these images have been taken by the SPHERE instrument that is mounted on the Very Large Telescope in Chile. And again, you can see exquisite features of spirals and also bars on the top image. So you can see that this is somehow barred in the middle, and this is somehow attributed to an inner disk that is mutually inclined. And actually, that's it's casting a shadow on the main disk that we see. And again, we're having spirals on the bottom. So asymmetries and most likely planetary induced patterns in debris disks are fairly common. Now, the thing is that with Hubble, what we see is visible light. So like I was saying, in debris disk, you have lots of things that are happening. You have a lot of leftovers, you have collisions. So typically you have a collection of bodies that will range from kilometer-sized bodies like asteroid comets, and via a collisional equilibrium and a collisional cascade, you will have all the sizes down to micron-sized dust grains. And these micron-sized dust grains, they reflect visible light, and it's thanks to this visible light that they reflect that we can see those with Hubble. Now, the problem is that these small grains, they are very much affected by radiation effects from their host star. So you will have a collection of effects, one of them being what we call the radiation pressure. So these grains will tend to be progressively blown away out of the system. You had what we call the pointing Robertson drag, which effect is to have this grain progressively spiral onwards onto the star. And of course, collisions. So in the end, the end result of it is that in these images, as you can see, these little grains are everywhere. And aside from specific cases like Fomalhaut, for instance, it can be extremely difficult to distinguish anything and any gravitational pattern in these images. So one of the strategies that we can follow is to go and take a look at bigger grains, because they are less affected by these effects, and they will stay closer to where they are produced. So to see bigger grains, now we're entering the realm of infrared astronomy. We are not seeing reflected light, reflected visible light anymore, but we are seeing infrared emission from these grains. So here you have again Fomalhaut, as seen with Hubble on the left, and on the right, this is the view of the same system, but seen with the Herschel Space Telescope and with the PAX camera at 70 microns. If you want kind of a rule of thumb, the grain size that you see is similar to the wavelength at which you're observing. So here at 70 microns, we're going to see grains of several tens of microns, hundreds of microns. So you can see, we can see different things in there. So you can still see somehow that the star is not exactly at the center at the geometrical center of the disk. You can also see something that is new as compared to the visible light. We can see what we call a pericenter glow. You can see that the part that is closer to the star is brighter. And that's an effect that we see at these wavelengths. And it's simply a thermal effect, the fact that this part of the disk is closer to the star. Now, Fomalhaut is interesting because it's very close to us. So with Herschel, we had like very good resolution. However, this is the view of Beta Pictoris, again, compared between Hubble and Herschel. And suddenly, it's kind of blobby. So there's not much you can really do with that. And I have other examples here, always comparing Hubble and Herschel. And we have blobs. So that kind of complicates matters. And the reason is, oops, what am I? Okay, let's not stumble upon the chair. So the resolution will depend on the wavelength that of your observation, but also on the diameter of your telescope. And so because infrared wavelengths are typically 100 times greater than visible light with Hubble, if you wanted to get the same level of details with a Herschel than you have with Hubble, you would need a mirror 100 times bigger, about 800 feet of diameter. So that's not in the realm of what is possible. There's a solution in there that is interferometry, and which was brought with ALMA. So it's maybe not obvious, but that's me. I'm in my scarf, I'm in my hat. It was freezing cold up there. We're at about 15,000 feet of altitude. It's crazy how we take oxygen for granted. It's not. But the fact is that at this altitude, we're having less atmosphere. And so radiations, we're getting more radiations. And that's exactly what we want. So what you see behind me is a collection of antennas. And actually, I'm standing in front of the center. So it's about a dozen of 10 meters antennas. And then you have a collection in total of 66 antennas that are 12 meter in diameter, and they are scattered all over this plateau in the Atacama Desert. And what we're doing here is that we're using radio wavelength. So it's going to be 10 times in terms of wavelengths, it's 10 times greater than what Herschel was doing. And if you understood what I was saying before, you could tell me, but hey, why are we going to that? Like, what of the resolution? You're going to need even bigger telescope. And the result is interferometry. Also, because at these wavelengths, you do not need mirrors, but you can go with antennas. It's much easier to, with a given sum of money, it's easier to produce a number of antennas. You produce a greater number of antennas than if you had to produce actual mirrors. So interferometry. So what is it? So technically, we're going to combine the signals from pairs of antennas. And if you have two antennas that are separated by 1 kilometer, it's the equivalent of an antenna of 1 kilometer of diameter. Not in terms of collection surface, of course, but in terms of resolution it is. And what we can do is that we can combine, we can have all these network of antennas and all combine them together. And we're going to end up with a map like this. So it's not a direct image of the sky. It's more, so for those of you who are familiar with this, this is a Fourier transform. And for those of you who are not, the best way I found to explain that is that it's pretty much a map that tells you yes or no, is it something that big here? So you take a pair of antenna, 1 kilometer, separated 1 kilometer, and they observe that portion of the sky. Yes, no, there's something that big with the resolution it corresponds to. Is there something that big here? Yes, no. And then the Earth will rotate. So you get a different angle, and you get a different angle, and every time, yes, no, yes, no. And then you take another pair of antenna, maybe this time you separate them like 500 meters. So you're going to explore another scale. There's going to be another resolution that's going to correspond to that. And so you cover all of that, and you have this map, and you do the inverse Fourier transform of that. And there it is. We have a disk. So this was the very first observation I had with ALMA. I cried when I saw that. And even though there's presumably a galaxy right in the middle of the disk saying like, hello, I'm messing things up, I was still very happy with it. And just like with formaldehyde, you can see that in this case, we see the star. It's actually this, you have the little white lozenge, which is the geometrical center of the disk. And just next to it, slightly offset from it, you have the star. So it's a disk that is intrinsically elliptic. And yeah, my hunting mission is accomplished. It's a little bit like being CSI, but in space. You're looking for prints and you want to know who the culprit is, and you have you give a profile. It should be like this, not more massive than that, etc., etc. So this is what I do. Again, to give you an idea and compare, these are three images. So the first with Hubble, the second with Herschel, and finally what ALMA brought to that. Formaldehyde again. So formaldehyde is so close and it's so big that we actually, it wouldn't fit within one field of view of ALMA. And so it had to be taken like first there was the northern arc that was taken, and then the southern arc. And so we can have a complete image of that. In that case, what is very interesting is that you can still see somehow that the side of the disk that is closest to the star is a little brighter, but not as bright as the side that is opposite. And that's a phenomenon that is called apocenter glow. And this time it's not a thermal effect like the pericenter glow was with Herschel. It's more a dynamical effect because things are at apocenter, so they go slowly or on the orbit. It's like a traffic jam, basically, a traffic jam of grains. But having this kind of exquisite image really tells us a lot about what kind of planet could have shaped that, much better than the Herschel image. Although in the case of formaldehyde, they are all exquisite, I have to say. In the case of Beta Pictoris, so this time we can see exquisite resolution with ALMA. So it doesn't look like a blob anymore. And you can see that you have a side of the disk, the right. So on the top panel, here on the right top panel, you can see that you have a side that is brighter than the other. So this is a density map. So these are millimeter sized grains, but I would like to draw your attention on the map that is underneath. And that's also one of the things that you can do with ALMA is to look for gas emission. So technically, you put your receptors, you can split your receptors into spectral channels. If you just want to go for continuum emission, you don't need lots of those. But if, for instance, in this case, you want to take a look and see if there's gas, you can use a mode and actually divide your reception in a much larger number of spectral channels so that you can catch gas line emission. And in that case, carbon monoxide was found. And it's actually quite surprising in such an object because we're past the protoplanetary phase. All these objects I'm showing to you, they're past the protoplanetary phase where, you know, there's a lot of gas and planets are forming. In all these objects, planets have formed, are supposed to have formed, and gas has left the system. This is also one of the reasons why to observe any one of those objects, it takes about dozen hours of ALMA time, whereas if you want to observe a protoplanetary disk, it will take 5 minutes of your time. So every time you have to ask for ALMA time, you really need to argue that you have the most spectacular system, and you're going to have like so many good results with that. And so in this case, we have found that gas, and it actually tells us that this is not primordial gas. This is secondary gas, and this responds somehow to the overdensity that we're having on the top panel. So what it tells us is that we're having a population here that is kind of trapped there and colliding actively, and there's a carbon monoxide that was trapped onto these bodies and ices that is being released. And that's very interesting because that tells us about possible, that gives us possible an explanation about planets in there. So in the case of Beta Pictoris, there's a planet that actually has been discovered and has been found responsible for the secondary inclined disk. But the planet that would be involved here is much further away. We're trying to target it with direct imaging, but it's still too small. It would be somehow Neptune sized, so we're not there just yet. And what would be interesting, especially what this gas indicates, is that it would have migrated outwards in the disk. And when a planet migrates, it will tend to capture asteroids into stable positions. We can think about Trojans with Jupiter, a little bit like that. So that tells us there's a clump that might be linked to this kind of phenomenon. This, again, another blob, and suddenly among the blob, we're having this exquisite disk with a gap in there. That one, I remember working on it. It was super interesting because we could really work on the size of the gap and its depth, because what we could say is, okay, we have a gap that is that wide. So if we want a gap that wide, we should put a planet that big in there. And suddenly we realize, oh, but it would clear everything. Like, obviously here we're still having something, the gap is not entirely clear. It's deep, but it's not entirely cleared. And so we try different scenarios, and actually we managed to have a much better match to the observation by comparing that with the effect of a couple of Neptune-sized planets in this gap. And that's also very interesting because it's a kind of, makes us question the paradigm of planet formation, because in that case, that would mean that we have planets that have somehow formed at much larger distances than we thought was possible. So that's work in progress. And this one is actually not a unique case. We have other cases actually. So on the bottom row, the second one, so this one is a little bit inclined, so we can't see it as well. But again, it's a wide disk with a gap, just like HD 107-146. And again, with the third one on the bottom, thank you. Again, not really obvious, but when we do some azimuthal integration and everything, we can see that there's a gap. So here is a kind of a small collection of disks we're having. There's also on the top right, the two images on the top right are H3799. This one is super famous because there were multiple planets that were directly imaged in there. And these were observed with ALMA. And we thought there was yet another planet beyond. And so I got additional observations with that, and the answer is still very unclear, but well, that means I still have a job. So, so I think that's it for the ALMA part. So I would be happy to take questions at this point, and then we can see how we proceed if you want to hear more about the rest.
Not getting red on my microphone, so is it working? Okay. So we have helping us with technology tonight. We have Terry Lappin and Pete Hermes and Bob Rose. And so they're going to be helping with questions that we have on Zoom and on Facebook. So Pete, can you tell us what questions you have on Zoom? Nothing on Zoom at this time. Terry, do you have some on Facebook? There's one. Okay. What's your, you don't have a microphone, do you? Here.
Yeah, thank you, Doctor. Just so you know, we had up to 17 people on Facebook from Kentucky, Minnesota, Maryland, and Arizona. Anyhow, one question that did come up midway through the first part of your presentation: asteroid belt can be a planet which was destroyed by collision. I assume that's referring to our asteroid belt.
can this be a planet that was destroyed? Well, in that case, it's going to be probably short-lived because you're going to have, and I'm trying to remember some simulation that were carried out by one of my colleagues in France. And typically, when you have you have a collision like that, you tend not to have a smooth disk like the one we see, because you're going all the bodies are going somehow to go back to the point of impact. So you're more going to having like somehow a smooth structure, but and a big blob. That would be my answer. If we see this kind of structure, I will be tempted to say, oh, there was a collision. But for a whole belt and things as smooth as what I've shown, no, I don't think that's possible.
Okay. Thank you. And I'm sorry that was Facebook questions rather than Zoom questions. So Terry's going to do Facebook. Oh, okay. Pete's doing. Pete's got everything to do. Okay. There's nothing on Zoom.
Actually, I think there is. But I can't see those because I can't find my pointer. Okay, but there's a second one that just appeared.
So there was a comment about using the cursor.
HRD 799, if I can talk a little bit more about it. So HRD 799, it's a little bit younger, broader, more massive version of the solar system. We know that there is a belt that is analog to the Kuiper belt, which is the one we're actually having in the images here. But and then we're having these 4 planets, and you can see there's a little insert that shows you where they are in comparison with the Kuiper belt analog. And then located below, how would you say that? I'm sorry. Sometimes words are still difficult for me in English, despite practicing for all those years. You also have an asteroid belt. So it kind of mimics the structure of the solar system. You have an asteroid belt. You have these 4 giant planets that are between 5 and 7 Jupiter masses. And then you have this Kuiper belt. So it's more extended than the solar system. I think the main belt is at about 200, between 150 and 200 astronomical units. For reference, the solar system Kuiper belt is at about 50. So it's 3 times wider. Planets are also much more massive. Also, because they are very massive, there is a necessity for them to be in what we call resonance. So they are what we call in a double Laplace resonance. Although I think for planet E, we're not quite sure exactly which resonance it is in, but we have a Laplace resonance between planet B, C, and D, which means technically that when planet B is achieving 1 orbit, planet C is achieving 2. And when planet C is achieving 2 orbits, planet D is achieving 2. And this is the kind of configuration that we can see in the satellites of Jupiter. And this ensures that every time one of them is at conjunction, the other one is at least 60 degrees away and is not perturbing it. So that creates a stability in this system. Planet E, I think we're still debating exactly in which resonance it is, if it's also 1 for 2. But it is in resonance. We're still not sure which one, I think. But yeah, you need that to have a system with such massive planets being stable. So, yeah, and if there's anything they want me to say about the system, I don't know.
Okay. Was there any other part to that question, Terry?
I don't know. Do you have a question? A question over there.
Was there any? Okay.
Oh, sorry.
So are we going to audience questions now? Okay.
So how long do these orbital stabilities last in these systems?
Honestly, I've been trying to run those, and you really need a specific set of initial conditions for them to be stable long term. Because I've been trying to run those orbits. I was curious, and I took a look, and it was really difficult to maintain that. Although I'm not quite sure. I think you really need a specific set of initial conditions. So I don't know how long they will stay like that. Chaos is chaos is a thing.
They just, if they're not stable, then you have to catch them in our temporal kind of time. So do you have any idea what percentage would be stable for us to actually be able to study them?
Oh, no, I have no idea. I'm trying to remember some papers by dynamicists in Hungary who did that, but I can't remember the numbers. I'm sorry.
Okay, other questions? Raise your hand.
One up there.
So I'm on my way.
Is there any mechanical model for how a planetary system that has resonance, how it arrives that two objects are, one has a period of exactly twice the other, and if there's another which is 4 times, like how does an initial swirly thing converge on a resonant state?
So the idea to get planets in resonances is migration. They're going to, so we know that planetary migration is a thing. And usually when they hit this kind of stable positions, they tend to stay in there. So this is how these resonances are formed. We don't suppose that they form in resonance, if that's what you mean. We believe it's a migration mechanism, and then they hit a stable state and they like it and they stay there.
Okay, thank you. We have another question.
Yeah, you were saying you could detect CO using ALMA. Is it totally radio frequency, or is there a hyperspectral content on it, or is it just totally radio frequencies?
I'm not sure I understand the question. Can you?
You said that you could detect CO using
Yes.
ALMA, right?
Mhm.
But ALMA is total radio frequency spectrum. That's what it is, right? That's where it operates. It's there's not like a hyperspectral instrument on it or any, they're just radar antenna, correct?
So technically you have different settings with how you can set your receptors. So you can either ask it to be at low spectral resolution. So this is what you will do if you want to detect continuum, but you can also, you have four spectral windows.
Oh, okay.
And the one that is on the frequency of the line you expect to detect, you can ask for it to have like a high resolution. And in this case, well, depending on how wide your line is, you can expect to cover it with, usually we're setting this so that we can cover the line with 5 spectral elements. Does that make sense?
Yes. Okay. Thank you very much.
Okay, other questions? If you will raise your hand, okay. I'm just looking and making sure there's no one else in the back before I come down to the front. And I'm on my way to the front now.
Yes, Professor, another Facebook question from Phil. How has the cyber attack on ALMA yesterday, I don't know if it means yesterday, impacted observing?
I have no idea. I saw that on social media and they're apparently shut down operations. So I don't know exactly how this is going to impact. They also had to shut down for a while during the pandemic. So I guess this is not a, I would say this is not an unknown situation in the sense that they have to shut down in emergency. But I have no idea. I have not communicated with my colleagues up there about this.
Wonderful. Another question? Okay, looks like
Okay.
we're through. Were you going to say something else?
No,
Okay.
that's it. So I think I can go on. And how much time do I have left? I don't want to take up your time, too much of your time. How much should I aim to? Yeah. Okay. So now we're going to go towards the habitable zone. We've been taking a tour in the outskirts of planetary systems with Kuiper belt analogs, and now we're going to go in the innermost parts. I talked briefly about it, but one of the challenges in the next decades to come will be to identify Earth-like planets in the habitable zone of their host stars, and also to directly image those so that we can potentially know about their atmosphere and also if they contain liquid water and biomarkers. So that's a real challenge. So here is H3799 seen with the LBT. So the LBT is in Arizona, is at Mount Graham. It's possibly the largest telescope on Earth at the moment, despite not being very much advertised as such, because it has these two giant mirrors that can be recombined. I'm going to come to this quickly. But this is the H3799 system. And I told you these planets were kind of analog to the giant planets in the solar system. And what we would like to seeing one of those planets, so we detect those through direct imaging. And one of the challenges would be that we need to overcome, and this is a comparison to tell you how difficult this is that to detect a planet, to detect Earth near the sun, it's like spotting a firefly next to a lighthouse. So it's going to be complicated through Earth's atmosphere. We're going to need a space telescope, and there are two concepts that have been developed by NASA. One of them is called LUVOIR. Okay, so kudos to my colleagues who worked on LUVOIR. I tend to prefer HABEX because I worked on it, and I really like the star shade concept of it, like this kind of thing that just opens up in space and is going to mask stars. I really like it. Turns out that NASA has opted for is asking us now to work together and to have a combination of those. So it looks like we're going towards a HABEX concept, but with a larger mirror, and we're going to have things detectors that we're going to develop with the people in LUVOIR. So now, do you remember the firefly planet I was talking about? So now try that in fog. And that's exactly what zodiacal dust does. So you might be familiar with the zodiacal cloud. It's this collection of small micron-sized dust grain that is in the habitable zone, and that so on the bottom image you can see. So you have the Milky Way in the middle, but you also have the zodiacal light there, and this adds fog to our observations. And as you can see on the top panel, on one side, on the left side, we have a lot of fog. And on the right side, we have less fog. And suddenly you can see a third planet appear closer to the star. And that's really a challenge, because this dust could cause confusion for EXO-Earth imaging missions. And we want to quantify that. So we can see that, so 1 ZODI is the quantity of dust we have in the solar system. And we can see on the right panels that pretty much when you go up to 10 ZODIs, if you have one planet, which is the dot that we see on the observation, it's still somehow visible. But as soon as you move on to 20 ZODIs and up to 100 ZODIs, you don't see the planet anymore. And because you can have some resonant clumps in this dust that will create confusion, and you might think, oh, I have a planet, but no, it's just a clump. You can still say things about your planet because the resonance configuration, but somehow what you want is to get photons from the planet itself. So it's a little bit tricky. And this is where the Large Binocular Telescope went into a mission. So honestly, I've been to ALMA, I've been to the VLT, but the LBT takes the cake. I mean, I've never been that impressed. I arrived at the bottom of the telescope and it was like, wow, so big. And just to give you a little bit of perspective, this is one of the 8-meter mirror going up the mountain. So you have a human being for scale, just right there. So yeah, it's truly, truly big. The LBT has adaptive optics, which means we compensate for the effects of the atmosphere. So this is what you could see without correction. And suddenly when you add correction, you can see that this kind of fuzzy blob is actually a triple star. What we have also is the capacity to actually go in the habitable zone. So this graph, technically, I'm just going to skip quickly over it, but it just tells us that you cannot detect zodiacal dust with infrared, like we're doing. Let me rephrase that. I was telling you that when you have a debris disk, you take a look at your star and the spectrum, and suddenly you have a slope, and in the infrared, boom, you have a bump, and you know there's a debris disk there. But it doesn't work like that with zodiacal dust because it radiates at shorter wavelengths, and that falls right with the spectrum of the star. It's not really distinguishable. So we really need to visually see this dust. We cannot do simple photometric measurements. And so we need a resolution that goes down in this green circle. So this is the system of H3799. And we need to go in that green circle there. And I'm going to skip quickly over that, just to, there we are. Yes, we're going to take a look at about 10 micron emission. And if you remember what I told you, if you go to a wavelength that is 10 times bigger than 1.7 micron planet C was observed there, you're going to need a telescope that is much, much bigger to have the necessary resolution to observe at the same resolution at 10 microns. This is what we're doing in interferometry again, but this time with the LBT. And this is why actually I'm saying that this is the bigger telescope in the world, is that because, so a lot of people, when they see that, oh, you have like 2 times 8 meter, but with the power interferometry, what I see is a mirror of nearly 23 meters. And that makes it one of the precursor to the extremely large telescopes that are coming up in the next decade. So you have the mirror on each side, and in the green box on this image, you have an instrument called the LBTI, which stands for Large Binocular Telescope Interferometer, and this is what's going to recombine the signals. So we're doing what we call nulling interferometry. That allows us to actually cancel the light of the star. So here you have kind of a definition of a constructive and destructive interference. You have like 2 balls that are dropped in the water, and you can see that they create ripples. And when these ripples can cancel one another or just add up. And this is what we're going to do with nulling interferometry. So you have a star, and you have this double slit experiment. So on the screen, you're going to have ripples. And right at the center, you have the peak where your the peak of your ripple, constructive interference. But what we're going to do is that we're going to introduce a phase shift on the light path, on the second light path, so that it becomes a destructive interference. And so we can mask our star. And so everything that is around the star, like dust, appears. And the star is completely masked. So we can identify extended emission. And this is what we do to detect exozodies. Currently, the LBTI is the most performant instrument to detect those. It goes down to a sensitivity of about 10 zodies previous instruments like WISE were going for much larger quantities of dust. The Keck interferometer in blue on the left panel went for about 100 zodies, but really with LBTI, we can go down to that level. And what we found was super interesting for NASA, because what we found is that we had detections, but mostly we had non-detections. And that's really interesting, because that tells us that the median level of zodiacal dust for Sun-like star is about 3 zodies. So that's right in the range that is okay for us to observe exoplanets. So we can go for it. Also, there's a clear difference between stars with and without an analog to a Kuiper belt. You are more likely to have an exozody if you have a Kuiper belt, and that's no coincidence. So yeah, EXO-Earth imaging is generally possible. These are a bunch of our detections. So with several hundred times the zodiacal dust. But technically, it's really not a coincidence if you're having more chances to have an exozody if you have a reservoir of if you have a Kuiper belt or an asteroid belt, because these act as reservoir. This dust cannot subsist close to its host star as it is. It's micron-sized dust grain. It's going to be either blown out or spiral onwards to the star or being collisionally destroyed. So you need to replenish that, and you cannot replenish that by collisions in situ, because a population like that would not survive long enough. So you need really to bring things from far, far away. And I'm going to get to that in a second. This is a little game that my colleague Steve played with, and he was just like, hey, how about from another planet? What if we were on a planet that was like Epsilon Eridani was about 300 times the zodiacal dust? Would we even be interested in making observations with that? That would really impede on the possibilities to observe the sky. So that's kind of a little philosophical question there. Okay, so the origin of exozodies. So like I was saying, bodies need to be brought from beyond the ice line, so asteroids and comets, and they need to be brought in the innermost part of a system, and then they can disrupt, they can also evaporate, and they leave dust there. Also, most interestingly, they can also bring water and organics to Earth analogs, because when you're beyond the ice line, you have a lot of chemistry that can happen on the surface of these grains. Very interesting organic chemistry, and it can produce. So this happens during the protoplanetary phase, as we understand it. And then these organic molecules are then trapped onto dust grains and in ices. And so when you bring them back in the habitable zone onto Earth analogs, then you can unlock the potential to get life. And so one of my specialty, and that's because I've been studying dynamical interactions between planets and disks, I soon found that it was applicable to all the possible ways you can bring back these bodies from beyond the ice line into the habitable zone. So I like to say that, you have cakes, you can have different kind of cakes, pound cake, rolls, brioche, blondie, Savoy cake. They all have the same basics ingredients in there. Then you have different recipes, but in the end you have a cake. An exozody is a little bit like that. So you need, for the ingredients, you need kilometer-sized bodies, like I was saying, a reservoir, and you need planets to interact with. And then you have a variety of recipes that can lead to an exozody. So they all have different flavors. I just got a grant from NASA to study these different flavors for the next 3 years. We hope that in the future, we will be able to directly see these flavors with EXO-Earth imaging missions in the system where we have a lot of dust. We would consider that not everything is lost. that we still might learn lots of things on underlying planetary systems. And that's on what I will be working for the next 3 years, and hopefully more, because I really like that. And then I'm just taking a tour of the different recipes, late heavy bombardment, like it happened in the solar system, change of configuration, and suddenly everything goes awry. Single catastrophic collision, that's the kind of thing that could happen. We have some spectral features that tells us it did happen in a couple of systems. Jumping from the reservoir through a chain of planets, jumping from planet to planet. I really like that one. Resonant phenomenons. So here we are. I talked to you earlier about the phenomenon, but there's a little video in the Jupiter satellites. Every time they light up, they're in conjunction and the other one is far away. Also a swing next to it, because I tend to explain resonances. I think kids are probably the most knowledgeable of resonances, because they know instinctively when they're on a swing that they need to push always periodically at the same time if they want to fly away. So it's the same with the resonances. You always have interaction in the same configuration, and if it's destructive, it tends to add up and things fly away. Or if it's stabilizing, that it stabilizes over and over and over again. Yeah, resonant phenomenon. So yeah, I couldn't do a presentation without showing one of those phase space diagram that my PhD advisor is so happy with. He gave me the taste for those. I love those. I think they're very useful when you know how to read those. Otherwise, it's just pretty. But technically, let me take you, when I see this diagram on the right panel, I'm showing you what happens in my mind with a little kind of movie. So you have a planet on the black orbit, and you have a planetesimal, like kilometer-sized body on the red one. And they are in resonance 5 to 2, like shown on the diagram. And this is what happens in my mind when I read this diagram. So the orbit changes orientation, it precesses, but at the same time it's deformed and it changes in eccentricity. It's particularly interesting when it's in that configuration, because it can get completely destabilized and ejected by a planet. And then it can produce, well, a comet and an exozode. The asteroid belt is also famous to have these resonant gaps. We call the Kirkwood gaps. It's kind of connected to the very specific nature of the solar system. It's highly non-generic, okay? The shortcut that people are using, oh, these are resonances with Jupiter, and they kind of expect this to happen all the time. But that's not the whole story. The whole story is that we also have Saturn, and then orbits tend to precess. And it's an overlap of mean motion and secular resonances that gives this. Jupiter alone could not do that, not with its current orbit. If it was a little bit more eccentric, it could do that alone, but not in the solar system. Quasi resonances, you're going to go from things that are super inclined and circular to coplanar and super eccentric, so it tends to come super close to the star. I think this is, yeah, it's source of most comets in the solar system, and that's because a lot of them are coming from the Oort clouds, so they are mutually inclined, and this is what can happen. So yeah, my conclusion slide. So the shape of debris tell us about content in planets, and they are currently difficult to access. We're lucky to be part of a system with the 1 Zodi level. We won't have any problem to characterize exoplanets in the habitable zone in the future. That's very good news. And also, exozodies equal exocomet equal transport of material in the habitable zone. So do these planets have more chance to have developed life on them or not? Give you the example of dinosaurs. I mean, like if you are constantly bombarded with stuff, like do you really have a chance to develop anything? And the other one, for those who recognize it, my husband worked on that attraction. He's doing special effects. This is Waterworld at Universal. You could have water worlds. Like, what is going to develop on that? That's a good question. And finally, because I like photography and I did those in the Atacama Desert, and I'm going to leave that here for the sake of, aesthetic. And I'm going to take any question that you might have.
Do we have questions from Zoom or Facebook for this portion? No? Okay, so do we have questions for people in the room? So yes, we have a question, okay? I will be there in just a minute.
Can you explain once more what a ZODI is?
One Zodi, the actual unit, or what it is, the actual definition of
Maybe both.
maybe both.
If there's more to know.
Okay, so you have in the solar system, you have this dust that permeates all the habitable zone, and that you can see in the sky as like this kind of light that is perpendicular somehow to the Milky Way. And this is dust that is left here by comets that are making incursions in there. As soon as they approach the sun, they're starting evaporating, and so they're leaving behind. These are dirty snowballs, so everything they have locked in there is starting to, well, it evaporates and it's left behind. This is also why we have meteorite showers, because it's when the Earth passes in the trails of one of those comets. And you have this whole population of small dust grain that is always present. Well, technically it's renewed. Okay, it's like you never go in the same river twice. This is a little bit the same principle here, and this population is regularly renewed. And so yeah, it's in the whole habitable zone of the solar system. And so what we call one ZODI is the quantity of dust pretty much that we have in the solar system. And so we're trying to measure that for other systems and make sure that it's not going to create too much fog for our observations.
Any other questions in the room? Okay, well, thank you so much, Dr.
Thank
Fairman.
you. My pleasure.
This is certainly interesting research, and we appreciate you coming. After you get some time with your next study, we hope that you'll come back and
Sure.
let us know what you found out there.
I hope to find interesting things.
Yes. Well, we're going to count on your finding something that will be fascinating. Okay, we have now another activity. We have some more awards that are going to be given. Some of you know that we have an astronomy fundamentals class. That's a 3-day course that the club offers to members. And we just had that class given and completed recently. And so Doug Smith, who taught the class, is going to give awards to the people who completed it. So Doug.
I also have an Astronomical League Observing Award to hand out tonight. Pete, come and get it. This is for his Messier Binocular Award.
Thanks, sir. Appreciate it.
And you get a pretty pin. Okay, so this is a long list of names for the people who finished the class successfully. So I'm going to read them off, and please come down and get your award. Do we want to do a group picture? Okay, so when you come down here, please stay down here behind me, and May's going to take a group picture, which will probably end up in the next bulletin. Ross Carnes.
Not everyone's going to be here tonight. George Carter. Hector Capato. Kevin Green. And Naomi Green. Susie Gunn. Sharon Hogan. Steve Irwin. Another no-show. Gladys Jimenez. Susan Jordan. Mary Lawler. Kay Lehman, I don't see her tonight. Paul Leroy. Mary Lawler. Which one are you? Oh, you're farther back. Okay. No Paul Leroy. Okay. Robert Reed. Sarah Russell. Ed Smith. Oh, a lot of no-shows. Surprised. Gene Solosky, that's you. I got two of them here. There you go. That's you. Keith Steinen. No. And Chris Wheeler. Oh, no, there's one after that. Robert Williams. Half the class didn't come. Okay.
Doug, would you get a one end or the other? And we'll get a picture.
Wow.
Doug did a great job. I just.
Yeah.
Hold your certificates up. Hold your certificate up.
Get in front of me. Whoops. Here, we gotta sit you down a little bit. Dude, I would have dressed different.
It was a great class.
Yes, great. Okay, thank you, everyone, and we're so glad people did that. Okay, now, let me see. Don't want to miss anything. I think we're about through here. Yes, we are. Okay. I wanted to remind you, so there's no breakout rooms tonight. There are refreshments in the lobby for people who want to stop by there on the way over to the observatory. And so it's and you're going to get to look through the 21-inch tonight. And and you can thank the astronomy students when you leave for helping you out with this. And we hope you have a great time with that. Also, I wanted to mention that we're going to do some stations at the back of the room after the meeting for people who are here and want to conduct some business. We have Susan O'Connor sitting at the middle table in the back, and she has calendars for people who've ordered them. And she also is our new member coordinator, so she can help give information to anyone who's a new member or considering being a member. We're going to have Terry Lappin, who's going to go up and be on my right. And Terry is going to help people with membership issues. And or anybody who's here who hasn't joined but would like to join in person. And then we have On my left, we have Bernie Stinger. Bernie Stinger, as some of you know, is our new Star Party coordinator for nonprofit and school star parties. And Bernie has a whole list of star parties that have been requested this month. And Bernie really needs help with that. So that we hope that some people, as they pass by tonight, will sign up for one of those star parties. He's got a list of where they are. And so you can see what's in your neighborhood or whatever and when they are. And also people, club members who are out there on Zoom, please consider, signing up with Bernie as well. You can email Bernie or you can call Bernie and sign up with him. And there's information in the newsletter to help you out with that. So thanks everyone for coming tonight. And we're so glad you're here. And we have, Eric is here. I didn't see Eric. Oh, good. So Eric is going to do the planet report, right? You've got one for us? Good. Eric, this is Eric Krakowsko. Dr. Krakowsko does a monthly planet report for us. And he's been out of, I think out of the country. And so hasn't been here for a meeting or two. And I'm delighted you're back, Eric. We post a planet report each month on the webpage as well. But Eric will give it to you verbally now.
Yeah, the two giant planets, Jupiter and Saturn, are really in the evening sky. Jupiter is not to miss if you look in the southeast, early evening, and south later evening. And Saturn transits already in the south at dusk, or just a little after dusk. It's 40 degrees high, and the rings are still 15 degrees open, but after a few months, you won't see that until 2028 because they are closing. Jupiter is to the east of Saturn, and it's now so bright. Just a month ago or so, it was the brightest it has been in decades, because it's just at the closest part of its orbit to Earth. And I've tried to see if I can see shadows from Jupiter, and sometimes if you go to a very dark side, you actually can see that. Well, there is a nice shadow transit from Ganymede, its largest moon, on the evening of the 9th. I think that's Wednesday evening. And if you look just after 8 p.m., then Mars rises in the northeast. It's really getting bright, and its color showing very nicely, the orange color. By the end of the month, it already rises at 6 p.m., so it's soon after sunset, and it gets brighter than Sirius. And on the 30th, it will be the closest to Earth, so that's when it appears largest in a telescope. At 17 arcseconds diameter, that's somewhat better than the average opposition. So it's really good for watching Mars in a telescope and look at the markings, and one polar cap is visible. Here in Tucson, it transits 83 degrees high, so it's hard to beat. And Mercury and Venus are not visible this month, but Venus starts to be visible in the evening just around the end of the month. So we'll have them around the winter and spring then. Uranus is in opposition on the 9th, and at magnitude 5.6. That's, for most people, it's just near the limit of the visibility, naked eye visibility. So in principle, it's a naked eye planet, but you really have to know where it is. It's also pretty high in the sky. At midnight, it's 74 degrees high. And Neptune is a binocular object, 8th magnitude. It's just very close to Jupiter, 7 degrees west of Jupiter. Every 14 years, Jupiter and Neptune really close together, and that's just this year. We have a minor planet, 20 degrees southwest of Neptune. That's also 8th magnitude. That's the minor planet Vesta, number 4. And then this month we have 2 special events. One is the Leonid meteor shower. That's usually around the 18th. And it's this time there's predictions that around 11 p.m. on the 7th 17th. There could be a outburst where you can see several hundred meteors per hour, which hasn't happened in the last 20 years. But the problem is the radiant in Tucson just rises around that time. So if that happens, you probably see meteors that just going across the sky for a long way, just grazing the atmosphere, but not too many. But if it lasts for an hour or two, by that time, the radiant will be higher. So we could be in for the show too. I don't know how long that radiant lasts, but it's best around 11 to 12 in the evening on the 17th. If can deal with the cold at that time. And then the most interesting event, of course, is the total lunar eclipse, which is on the morning before election. And it's centered around 5 a.m. and with a totality of an hour and a half, and then an hour before and after is always the partial phase. So it lasts from 3 o'clock till 6:49, and that's exactly sunrise. That's when the partial phase ends. And I like that because when the totality ends, the moon is still reasonably high enough and it's still dark enough, so you really can watch the red moon quite nicely. And then once the moon gets towards the horizon, maybe 6:30 or so, it dims and twilight starts. But that's really very nice to see the shadings on the moon. Otherwise, when the moon is up in the night sky, it's so blinding, it's hard to see features. And so by sunrise, the partial phase will end, and that's 9 minutes before moonset. So the moon is around the Tucson Mountains, very low at that time. There's a second magnitude star to the 10 degrees north of the moon during the totality visible. It's Hamar in Aries. And the special thing about this eclipse, that Uranus is only 1 degree to the east of the moon. So it almost means that you can see Uranus naked eye during full moon. And that's probably the only time in life you really can see that. So actually, the moon will get closer to Uranus, and after eclipse, at some parts north of here, it will actually get occulted. But at our place, the moon has already set by then. So they will be nice to watch. It's also easy to find because there are not many 6 magnitude stars just 1 degree east of the total eclipsed moon. The southern limb of the moon will just go across the center of the umbra. So in the mid-eclipse, the southern part of the moon, that's the center of the umbra, that will be the darkest part. The next significant lunar eclipse will be in 2025. So if it's cloudy, we'll have to wait a while, but I think the weather forecast is good for now. So happy observing in the morning, and I'll get up early even if I don't like it.
Thank you so much, Eric. It's always nice, especially to hear the planet report, but it's really nice when you have the extra things like the meteor showers and especially an eclipse. So hopefully we will get to see those. Anyway, so thank you so much for coming tonight. We enjoyed having you here, and please go look through the telescope for Stuart, and then you can let us know. You can email people, or you can, at the next meeting, let us know what your experience was like tonight and what you were able to see tonight. So thank you so much for coming, everyone.